Okay, continuing on from where we left off in our Laplace transform playlist, we have this formula that we found a few videos back that if we want to take the Laplace transform of some shifted function, f of t minus c, times the unit step function, then that's just going to be e minus cs times the Laplace transform of the unshifted f of t function. And just as a quick review, we have our graph of the unit step function, or the heaviside function, over here to the right. And it's just a function that it takes on the value of 1 at some point c, and then everything to the left, everything less than c, it takes on the value of 0. So with this formula in hand, we're going to do something just a little bit different. We have the formula for the shifted function. What we want to do now is find what happens if we had to do this for the unshifted function. So what we want to do is we want to find the Laplace transform of just f of t times the unit step function at c. And it may seem like this is simpler, but it actually makes it a little more complicated because it works so nice with the shifted function. So what I'm going to do with this is we'll just use our definition of the Laplace transform. So we'll write it as an integral from 0 to infinity, e to the minus st. Then we're going to have this f of t and the unit step function. And this is actually pretty similar to what we did in deriving this formula. We're just going to use, to start with, we're going to need to deal with the unit step function. But noticing again that it zeroes out because the value of it's 0, everything less than c. So what it's going to do is zero a part of this integral. And actually what we can do is change this lower bound so it starts at this point c, just because everything to the left of it's 0. But then going back to the graph, you'll just notice from c to infinity, the unit step function, the value is always going to be 1. So I can actually just cross this out and turn this into a 1, and that's going to simplify things for us. And now this isn't so bad. The only problem really we have is this lower bound, because we can't really put this in terms of a Laplace transform until our bound is back to 0. So what I can do is a substitution for that. And I think for the substitution, I'll use the variable x. And if I write my x as t minus c, that's going to allow me to set this bound back to 0. We'll find our t value, so t is going to be x plus c, and then taking a derivative, dt is going to be equal to just dx. So then we'll just go ahead and make the substitution. So plugging in infinity here for t, infinity minus c, that's still going to give me infinity here. And then plugging a c in here, c minus c, 0 for the lower bound. So then for e minus s, we'll plug in our t value, which is x plus c. Our f of t is going to become f of x plus c, and then we'll just have a dx here. Okay, now I'll take this and we can actually just rewrite this and split it up as we have the addition here. So I can write this as e minus sx times e minus sc. And then by doing that, e minus sc, that's actually just a constant value. So I can bring that out front of the integral. We'll just write that constant out front as e minus, I'll change the order and write it e minus cs. 0 to infinity, then we'll have this e minus sx, and we'll bring everything down. And from here, we don't really need to do this, but I'll just do it to make it clear. I'm just going to do a variable change. On the definite integral, we'll change everything back to t, and we'll do a rewrite. And then from here, we'll just notice that this integral here, this whole thing, well, this is actually just the Laplace transform of this thing right here. So we can actually look at this a couple different ways. I think we also could do, what we could do maybe to simplify it or make it a little clearer, is we could call this f of t plus c, we could call it some other function, g of t. So then writing this formula, we could do it two ways. I can write this as e minus cs, and then the Laplace transform of g of t, then I can use my capital F notation, we can write this as capital G of s, which just means the Laplace transform of this g of t function. And so we could actually just leave this f of t plus c there, and we could write our solution as e minus cs times the Laplace transform of f of t plus c. And so I'd say either of these formulas are fine. And this will give us our formula for the unshifted Laplace transform of f of t times the unit step function. Now before we finish up, let's just do one example using this formula. Okay, for my example here, what I want to do is look at the Laplace transform of t squared times the unit step function at 3. Okay, now to start with this, what I want to do, just notice that our c value is clearly 3 right here. Our first option, we'd really like to use this first formula. So we'd like this to be f of t minus 3. So as our first choice, we would like t squared to already be shifted like this, but it's not. So that's where we'll use this formula. And we just want to find out, we can just look at our t squared as f of t and use this formula. So what we need to find is we need to find f of t plus c, which is 3. So we want to find f of t plus 3. And so with the function just being t squared, what we want to look at is t plus 3 squared. So just squaring that out, we get t squared plus 6t plus 9. And so for our solution for this, we want this to be e minus the c value. So we want this to be minus 3s. And then we want the Laplace transform of this thing, our f of t plus c. So we want to find the Laplace transform of t squared plus 6t plus 9. But now for everything here, we can actually use, we have a formula that we found a few videos back for the Laplace transform of t to the n. And we had it with the gamma function, but we can write it in terms of the factorial as n factorial over s to the n plus 1. So using this, we'll bring down our e to the minus 3s, the Laplace transform of t squared. So for the Laplace transform of t squared, our n being 2, we end up with 2 factorial. That's just going to give me a 2. And then s of n plus 1 is going to be s cubed. And then for the next one, we'll have our 6. We can look at this as a 1, our n value of 1. So 1 factorial is just 1. And then 1 plus 1, so we'll have s squared for this term. And then for 9, we can look at 9, the same thing as 9 times t to the 0. So our n value is 0. 0 factorial is going to be 1, so we're going to have this is just 9. And then if we plug a 0 in here, we just get s to the 1, or just s. And so our solution for this Laplace transform is just going to be this thing right here. And that's all there is to it. So I think we'll do one more example with the unit step function on the next video, and then we'll continue on to more Laplace transforms after that. Thanks everyone for watching. Have a good day.